Professor Ghassemi has been a wonderful part of the WIDS team for the past few years. She gave an outstanding talk at WIDS 2019 that we're featuring here regarding machine learning in healthcare. Professor Ghassemi was also on the career panel at WIDS in 2019, and she followed up with a wonderful WIDS podcast episode where she gave some insights about her career path and shared thoughtful advice for students and others in the field. Professor Ghassemi has been a key part of the WIDS Datathon team for the past 2 years as well. This Tech Talk from WIDS 2019 gives some great insights about the promises and challenges with machine learning in healthcare, such as with the biases in dealing with such data. In fact, we like this talk so much that we created a shorter version that is shared with secondary school students now through our WIDS educational outreach.
Welcome, Marzyeh.
Hi, everyone. I'm Marzyeh Ghassemi, and I'm a professor at the University of Toronto and a faculty member at the Vector Institute. And I'm going to talk to you today about learning healthy models for healthcare. So you might say, well, why would I even try to work in healthcare? Well, there's the reasons that prior speakers have suggested, right? It's a big industry. But when I was a PhD student at MIT, I spent some time with the friends I had who were doctors doing rounds in the ICU, and I found that the patient would come in and doctors would have very different opinions about how the patient should be treated. And so even if they were in the same hospital, two different clinicians might say, I think that this patient should be treated in this way or that way. And I thought, well, if we want to improve healthcare, then we need to be able to create evidence. And you might say, well, don't we already have evidence, right? Isn't this something that already exists? But I'm going to ask you now, how much do you think we really have? And I'm asking that because we don't even know what it means to be healthy. Think about that. We define being healthy as an absence of interactions with the healthcare system. You are healthy when there is no data on you. That is our standard approach right now. And so if that's where we are, how do we make decisions about how to treat a patient? Well, right now we do randomized controlled trials. So you recruit a study population, you have 2 medications maybe, you learn a rule with statistics or machine learning, but the question I want you to think about is, does that rule generalize? And for whom does it generalize? So pop quiz, right? Fun facts time. So randomized controlled trials are the gold standard in the field, right? Rct Backed Treatments. How many of the treatments that are currently used in hospitals do you guys think are backed by an RCT? You want it to be high, right? You want to say like 80, 90, 100. No, it's not. It's very low, actually. And this is not because of malintent. This is because randomized controlled trials are very hard to do. They are expensive and they are challenging to run. So now let's take treatments where we do have randomized controlled trials. Asthma is very common. It's a chronic condition. How many of the people who currently have asthma, they're being treated for asthma now, do you think would have qualified? They would have been in the inclusion criteria for the RCTs that were used to design their treatments. Again, you'd like this to be high, right? You want to say, well, most people who have asthma and are being treated, you could have included them in the RCT, right? But most of them wouldn't. So 94% of people who are currently being treated for asthma would have been in the exclusion criteria for the randomized controlled trial used to design their treatment. So clearly this data is biased. And again, this is not because of malintent. This is because when you're trying to look at some sort of mechanism, you would like for the population to be relatively homogeneous in specific ways, right? But this also means that we should go back to that original question. Does this data generalize, and for whom does it generalize, right? So what can we do? Maybe we can use machine learning. There's all of this data that's out there in the environment. We don't have to just look at electronic healthcare records, right? Maybe we can go beyond and say that all of this data really is health data, right? Maybe we can learn what it means to be healthy. But healthcare has been around for a while, and so has machine learning. Why haven't we done this yet? We haven't done it because it's really hard. This data was not gathered to answer a hypothesis. That's what an RCT is, right? It's exhaustive providing care. And because it's the exhaust of providing care, it's secondary data. And so what that means is it has all of these biases that are really hard to work with technically. It's heterogeneous. So you have text data, vitals, labs, sampled at very different frequencies, some over days, some over months, some over years. You also have this kind of sparsity that's really hard to work with in models, right? So things can be unmeasured because a sensor fell off, unreported because I ordered a lab value, it looks normal, I'm not gonna write it in the record, or there's just no follow-up. I can know that I gave you a medication, but not know how frequently you actually took it. This kind of uncertainty is so challenging to deal with. If I asked everybody in this room to agree on whether these are chairs, you could. It would be frustrating to label a bunch of chairs, but you could label them. But if I'm trying to decide in an example of data when somebody became diabetic, so I can show my machine learning algorithm what it means to transition to become diabetic, and I look whether somebody had a diagnostic code, an ICD-9 code in their record for diabetes, that code could be in their record because I'm catching diabetes now, but they've had it for a decade. That code could also be in their record, not because they have diabetes, but because I need to put it in there so your insurance will pay for this test to see if you have diabetes. So we're not even sure about our labels often in this space. And then the data, again, is very biased, right? You go to the doctor more when you are very sick. You don't often go when you're well. And context matters. If you write in a note that a patient is improving and they've been comatose, it's very different than if you write in a note that the patient is improving and they're on a diet. And so we have to be able to deal with all of those things. And I want to be very cautious to say, I have been contacted in the past by many people who say, well, I have the data. You have the machine learning. Together we can, anytime somebody uses a capital T when they say the, you should be very concerned. And so I want you all to say, have a note of realism about what you can do with data and machine learning. Because as prior speakers have noted, data is generated by a process, right? And that process often carries with it biases, right? And so, as a professor, right, like when I teach classes, I often show students these slides. So these are well-known examples in the vision community. These are two papers that I really like. One is Deep Neural Networks Are Easily Fooled, top row. And the bottom one is what I call Adversarial Pixel, which would be a great band name. But actually is showing that if you take state-of-the-art neural networks and you change one pixel, an adversarial pixel, right, an optimally chosen pixel, the neural network is very confidently wrong about ships being cars, horses being frogs, and deers being airplanes. So that's funny, because we can also ask the algorithm, why did you think that, right? And post hoc it can say, well, I thought that this husky was a wolf because you put it on snow, and I only ever see wolves in the snow. I don't see dogs in the snow. Why would you do that? But that post hoc justification works because we're all natural-born experts in vision and natural language processing and speech recognition. So if I show you an explanation for why I got it wrong, we can all giggle about the fact that we got it wrong because you put a husky in the snow or a cow on a beach. That's a real example, too. It's another test. Machine learning algorithms always get the cow on the beach wrong. They're like, why is the cow on the beach? But where none of us are actually natural-born experts? None of us are born experts in healthcare. And in fact, you have to train for over a decade, often, to be an expert in a subspecialty of medicine. And so when we have adversarial attacks that happen in a clinical space, we don't know what they look like often, and it's hard to understand how we might account for them or adjust for them. So this is something that is, I think, very challenging. And it requires domain expertise in a very unique way, even if you're not being adversarial. So this is a great paper from a few years ago. Rich Caruano at Microsoft Research took a bunch of hospital data and learned a model for people who are coming in with pneumonia, trying to understand who might die from pneumonia. And you can imagine this would be useful because then you could give them the most aggressive treatment. But the problem with that is it learned that people with asthma are at the lowest risk of dying from pneumonia. That should sound wrong because it is wrong, but you can understand why it would learn this because that was in the data. Because right now, if you come into the hospital and you have pneumonia, and you say, I'm an asthmatic, they treat you so aggressively, prophylactically, that actually in this data set, this very large hospital data set, people with asthma were at a lower risk of dying. And so you have to be careful because, again, we don't understand the generative process that creates a lot of this data, and you can't control it when it comes to something like healthcare. So I do machine learning for health. My research focuses on 3 broad areas: what models are healthy, what healthcare is healthy, and what behaviors are healthy. I'm going to focus mostly on what models are healthy, and when Margot comes to kick me off the stage, I'll quickly speak very briefly about the other 2. So most of the work that I do uses the MIMIC-3 ICU data, which is real patient data that's been de-identified and is available for anybody to use. So any academic who takes city training can go online, download this data to their cluster, and work on 40,000 patients worth of data. It's a fantastic resource. I recommend that people use it. So what's something you might want to do with this data? Maybe you want to do real-time prediction. I want to observe some amount of patient data and predict, will you need a drug? Will you die? Will you need an intervention by some gap time before a doctor could have acted? So I want to give you some sort of risk stratification. So what is something we tried really early on? The first paper out of my PhD, we thought maybe we can predict mortality in this population. And that's interesting because when people are really severely ill, we don't have a real-time score of how sick they are. Doctors sort of assess that in their heads, but mortality could be a proxy. And one of the things we thought is, well, a lot of people are using labs and vitals and all these signals. Maybe we should look at the notes. And nobody at that time had really looked at doctors' notes, not because they weren't available, but because they look like doctors' handwriting. They are not fun to work with, right? And so we made a model that took in these doctors' notes and represented them as topic vectors. So we have a couple of different ways of doing that. In the first paper, we used LDA, which is commonly referred to as topic modeling. So you can take all of this data, variable sizes, and create a single vector out of it. Now that you have every person as a distribution over these topics, right, and you've learned this in an unsupervised way, you haven't told it, learn topics that are correlated with mortality, just learn topics that generate the data that looks most like the data you've observed, you can check whether it's correlated with mortality as a sanity check, and it is. So topics that are protective, baseline mortality is right around 11%. Topics that are protective are cardiovascular surgery. I thought that sounded wrong, but when you ask the doctors, they say, no, that's right, because for surgeons, numbers count, right? So if people die, your numbers go down, and so they wait until if somebody comes in and says, I need cardiovascular surgery, and it's not an emergency, they actually send you home to get healthy for a little while, like diet and exercise before they operate. But then things like respiratory failure are really enriched for mortality. And the ultimate test is putting this into a regularized machine learning algorithm, right? And there's so many you could use, but what you want to see in general is that when you use a baseline, so the things that the doctors already are using, right? So these are gold standard acuity scores for the hospital, that's the blue line. That gets worse and worse over time, which makes sense because those models get stale really quickly. Our model in red gets better and better over time as more notes accumulate, and so it's more intelligent about what it knows. And when you put them in together, that's the green line, it does best. That's wonderful, right? So I was very excited about this, but that was now 5 years ago. A lot of work has followed this work. And these models, I would like to emphasize, are very complex and very clever models. These are high-capacity models. But we're not doing any better. That AUC is staying pretty static, right? That's our performance. Our performance is staying very similar. And so the problem is, just throwing a fancy, complex model at a problem in healthcare doesn't always work because, again, it's not respecting the data generation process, right? And so maybe if this performance bump is so small, predicting mortality is not something that can benefit from these high-capacity models because in a modern ICU, you often don't die unless the doctors turn off machines, right? You can keep somebody alive indefinitely. So another thing that we tried was trying to predict interventions. So you can process data in the same way, right? If we can turn all of your data into a matrix per person, Across a population, you're a tensor, and that's great because we have models that work well on tensors, right? We can use switching state autoregressive models, which are a kind of generative model, or we can use neural networks like short-term memory networks. They're a kind of recurrent neural network, or convolutional neural networks. And when you use different high-capacity models of these classes, it turns out that they do really well, right? So if we're looking at the generative model, using these state space beliefs improves your prediction accuracy for different kinds of medications or interventions, vasopressors, ventilators, plasma. Also, there's interpretability, right? So I can ask, why do you think that this state is most associated with needing a vasopressor? And I can take these values back to my clinical collaborator, and they can tell me why that might make sense or not. The same thing with neural networks, right? We can improve predictions across many different kinds of interventions, and then there are ways to ask a model, why did you think that that was an important state for predicting this particular outcome? And being able to leverage these kinds of tools in high-capacity models is really important. But now I will briefly segue into the why should we be cautious? This sounds really cool. But in health, there are questions beyond the obvious because humans are providing that care. And so we want our technology to help eradicate biases, not exacerbate them. So I was asked a while ago by a doctor, can we go back and check that 2014 paper, that first paper that I just talked about, predicting mortality in the ICU from the notes? So let's see, how well that does across different groups. And that's because biases are already part of the clinical landscape, right? So there's well-established literature that shows that biases in clinical data reflect the biases of society. So what that turns into is if we're building a machine learning model in populations that have high variance, you might see differences across variables where people often have biases. So we went back and tried to look at differences in prediction accuracy by group. And it turns out that you learn different enrichment in topics for groups. But that seems like maybe it's okay, right? Maybe it is just the fact that more women have COPD, chronic obstructive pulmonary disorder, than men. Maybe it is the case that more men than women suffer from substance abuse. But where it's not okay is when you look at prediction accuracies, and we find that people on public insurance have more inaccurate models. And this is if you do the thing that we all do in machine learning. We optimize for a global objective. We say we want to do best across everybody. But when you do the best across everybody, you don't do the best for some groups. And that difference is statistically significant in variables where we would not like it to be. And so one of the things that we need to focus on in machine learning for health is how we evaluate models. When we put recommendations in front of doctors, how do we use those? How do they respond to this information, right? What is the best way to tell a doctor that a patient should be given a different treatment? Because I can have the best machine learning model in the world, but if I surface that information and the doctor doesn't want to listen to it, or it doesn't make them more accurate, then I haven't done my job well. And then the last thing that I'd like to leave you with is, most of the time, hopefully, you're not in the doctor's office, right? So all of this analysis of hospital data, ICU data, it's what often people in machine learning for health tend to focus on first because it's where we have a majority of the high-capacity data. But really what we'd like is to be able to combine these different data types so that we can ask intelligent questions and answer them in a technically competent way. Right? So we have expert-reported data in the health record, there's self-reported data in a survey, and there's also all this passive data, right? If you consent to having your mobile phone report aggregates of information about you because you want that information to be put into a model, we could actually ask really important questions like, do depressed patients, expert verified, divide their time differently between home and work, and that's passively reported? Does the size and reciprocity of an interaction network help with your anxiety that you self-report? And does activity that we measure passively impact your mood that you self-report differently when you are postpartum that we can verify through a health record? So that's it for me. Thank you for coming, and I hope I've tried to impress you with how important these topics are and encourage you to get started in machine learning for health.